This is 7.2.2. We'll review unitary matrix operations. The transpose of a matrix. The transpose of a matrix given A of m by n is transpose is basically to move its row into a column. In this example, A is a 3 by 4 matrix. This is the transpose. It will become a 4 by 3 matrix. Basically, the first row is changed into the first column. The second row is changed into the second column. And finally, the third row is changed into the third column. Because of this, the following can be deduced. A transpose A will be A. That means if you have moved from row to column, when transpose again, the column will be moved to the row. So A transpose transpose is equals to A. What about operations of A plus B bracket transpose? The transpose is distributed. That means we can have open up the bracket and we perform A transpose first plus B transpose is the same as A plus B bracket transpose. What about the last one? C, where C is a scalar. And here, the scalar can be moved out. Basically, it will be the same as A transpose is the same as A transpose. We are not going to prove these properties, but you should know them by heart. A, B. Sometimes the acrosophy is used in place of a transpose, or we explicitly write T as for transpose is the same as B transpose, A transpose. And we have 3 matrices transpose, then it is the same as C transpose, B transpose multiplied by A transpose. This briefly reviews transpose of a matrix. We'll now discuss the inverse of a matrix. Inverse of a matrix only exists for square matrix, and for some square matrix are invertible, so then in this case we say that its inverse exists. When the inverse exists, we call the inverse matrix A to the power minus 1, the inverse of A. Then remember, A is a square matrix. Its inverse is also the square matrix of the same dimension. Then we can do multiplication because m by, for example, if it is a square matrix of m rows, then it will have m columns, and its inverse is also m row and m columns. Therefore, when this occurs and the inverse is multiplied with each other, the identity is resulted. The identity is of dimension m by m as well, and the identity, as you remember, means that it is a matrix with diagonal all ones of appropriate dimension. In the bottom left example, m is equals to the 3 dimension, or the identity matrix is a 3 by 3 matrix. Here we show to multiply the inverse of a matrix on the right hand side of A. Actually, we can multiply the inverse of matrix from the left hand side of A, and both will be equals to I. This is the property of inverse. So let's talk about more properties of inverse. The 3 properties of inverse include: if A has an inverse matrix, its inverse again is back to A. So A inverse and inverse again is back to A. You can convince this by yourself if you say that the inverse of A equals to B. The inverse of B is equals to A, and therefore when we substitute this, it will be A minus 1 minus 1. So the inverse of A, inverse again, is back to A. Now, The second property is we're going to prove this property. This property looks like the transpose property. What happened is now we have AB inverse, and this property states that it is the same as B inverse multiplied by A inverse. Why is this so? Let us study this equation here. Now if we make the appropriate bracket, B inverse multiplied by A inverse multiplied by A multiplied by B. This A inverse times A is identity of the appropriate size. Anything multiplied by the identity is the same value. So basically, we'll throw this away, and now we have B inverse times B. Therefore, we get identity. Now, if you perform another bracket, isn't this the same as AB multiplied by B inverse A inverse? And since the result is I, therefore, this bracket here that we have just circled is the same as AB inverse, giving us this property. Now for the last property, whether we perform A inverse first, then transpose, is the same as taking A transpose first, then its inverse. Why is this true? Recall the property of transpose. AB bracket transpose is the same as B transpose A transpose. Also, an identity matrix transpose is still the identity matrix, because identity matrix has only diagonal values. Additionally, it means that A inverse, if it exists, multiplied by A, this will be the identity. Its transpose is of course the same as, using the law of the transpose, is A transpose A minus 1 transpose. Now remember that this above was the identity, therefore this is also the identity. Now compare the second equation that we are going to examine. Instead of A inverse times A bracket transpose, we are doing it the other way around now. It's A first multiplied by A inverse transpose. Remember that this should give us again the identity, and the identity that is transpose still is the identity. Using the transpose law, we open up and we move the transpose inside. What we'll have basically is this. We'll have A inverse transpose multiplied by A transpose, and this will still be identity. Therefore, we now recognize if this is the matrix that we're interested in, its inverse is, I make a mistake. Let's try this again. Let's observe this equation. Let us now multiply by, on the right, by A transpose inverse. Therefore, it is I multiplied by A transpose inverse. Therefore, on the left hand side, we have A inverse transpose A transpose. We now recognize that this is equals to I, implying A inverse transpose is equals to A transpose inverse. Some common mistakes students may make is to assume that inverse is distributive. It is not distributive. That is, A plus B bracket inverse is not equals to A inverse plus B inverse. You can even try it for just A and B as a single real number. For example, 1 plus 5 inverse is not equals to 1 over 1 plus 1 over 5.